We know today that atoms are not the smallest bits of matter, that atoms themselves are actually comprised of smaller pieces. This was a surprising discovery for physicists about a little over 100 years ago. Physicists playing around with electricity and magnetism created what is called a cathode ray tube, or a CRT. A cathode ray tube consists of a glass, usually a glass cylinder, that's evacuated with the exception of a little bit of rarefied gas, so a small amount of some type of pure gas, like helium or neon or oxygen or something similar. So not just the air in a room, but actually a small amount of a specific type of gas. And then on either end, inside, there are metal plates that can be set to a very high potential difference, right? A high voltage is applied between the plates. And what physicists learned was that off the negatively charged cathode, particles would stream off towards the positively charged anode. And so, being rather ingenious physicists at the time, what they decided to do was they placed a small hole in the anode. And then further down, they placed another barrier with a small hole. So what they ended up doing was most of the particles would stream off the cathode and go back to the anode. But a small number of the particles would miss the anode because they hit the hole, pass through the second hole, and you ended up with a stream then, a beam of these particles. They wanted to know what these particles were. They noticed that they excited phosphorescent films. Photographic films would be excited, but they wanted to study what is that beam made of. So they put it through a couple of different types of experiments. One was to set it between two charged plates of known electric field difference, right? So you have a positively charged plate and a negatively charged plate. That creates an electric field. Going back to our electricity and magnetism earlier this semester, that creates an electric field inside between those plates and between that capacitor. When this beam interacted with that electric field, it actually got pushed away from, or accelerated away from, the negative terminal towards the positive terminal. So when the electric field was on, when the plates were charged, the beam went from traveling in a straight line to being bent. How much it was bent depended upon the strength of the electric field. So physicists, putting this all together, said, hey, force is equal to mass times acceleration. There's some particles coming off here with some mass. We don't know what that mass is. We're going to call these electrons, right? We don't know what the mass of the electron is. But we know that the force on the electron is equal to that mass times the acceleration. The acceleration they can measure here. They also know that the force is equal to the charge on that electron times the strength of the electric field. This equation comes about from the definition of what an electric field is. So putting these two things together, since they're equal to one another, the mass of the electron times the acceleration of that particle is equal to the charge on the electron times the strength of the electric field between those two plates. Not here, but the electric field over here. Rearranging this equation, what we see is that the ratio of the charge of an electron to the mass of an electron is equal to the acceleration over the electric field strength. The right-hand side of this equation we can measure. The left-hand side we don't know. But since we can measure the right-hand side, the charge on an electron over the mass of an electron is equal to minus 1.76 times 10 to the 11th, sorry, not minus 11th, 10 to the 11th coulombs per kilogram. What that means is that the mass of this electron particle must be very small to get such a very large number. We know that this electron is negatively charged because it's pushed away from other negative charges and drawn towards positive charges. So negative charges do that. So we know that the electron has to be negatively charged. And we know that because this ratio is so very large, the mass of an electron must be tiny. So this is the first hint of the presence of a particle called an electron. But the problem was this early experiment with cathode ray tubes did not give you an answer on what is the charge on an electron. It did not tell you what the mass of an electron is. It only told you what the ratio is. It took a later experiment called the Millikan's oil drop experiment, which I'll explain next, to come up with the actual mass of the electron. And once the charge on the electron. And once the charge on the electron was known, then we can use this relationship to find the mass of the electron. Millikan came up with a rather elegant solution to find the charge on an electron. What he did was he took two metal plates separated by some distance d and applied a voltage between them, which of course sets up an electric field. It's like a capacitor, but there's a little hole in one of the plates. He then very carefully sprayed an oil mist above the hole, and some of these oil droplets fell into the capacitor. Now, as you spray the oil out of a very fine aerosol can, what will happen is that those oil droplets will pick up excess charge. They might have one extra electron, two extra electrons, three extra electrons. It's very easy for those tiny oil droplets to pick up a few extra electrons or to miss a few electrons. So what Millikan did was when those drops got into the capacitor plate, two forces, now let's zoom in on that purple dot. Those little oil droplets, let's imagine it has one electron of net charge on it, right? So it doesn't just have one electron, but it has one electron more than it has proton. So the net charge of one electron exists on this small little droplet. It feels the weight of the droplet, right? The droplet, the oil droplet, is getting pulled down by gravity. But at the same time, the electric field is pushing up, applying a force upwards on the negative charge on that oil droplet. Right? The negative charge wants to be by the positive charge above it, and it's repelled by the negative charge below. So by playing around with the voltage between the plates, you can play around with the electric field strength, and you can vary the force F sub E. F sub G depends on the droplet itself. We can't really control the size of the droplets, but you can control the strength of the electric field. So what Millikan would do was he would change the voltage until a droplet was suspended between the plates. And he would try to find the minimum force necessary to suspend the droplets. So a droplet with twice as much charge would fly upwards because it would feel twice as much force. He found the minimum voltage necessary to suspend a droplet between the plates. So the two forces balance, where the force of gravity, which is the mass of the drop times the acceleration due to gravity, is equal to the charge on the droplet times the electric field strength. Rearranging that to solve for the charge on the electron, the charge on the electron is equal to the mass of the droplet times g over the electric field strength. Well, the electric field strength is not something you can easily measure for a capacitor, but assuming the electric field is constant, and it is between the plates of a capacitor, then you can replace that, right, with the voltage. Voltage is electric field times distance. So you can plug that into this equation. You have the plate separation D, which you know. You have the voltage between the plates, which you know because you're controlling that. The mass of the droplet, you look at it with a little telescope, or a little microscope, if you will. A little lens on one end, right? Another lens, look at with your eyeball. You're looking down with your eyeball. You can see these little droplets will look like little spheres. By measuring the size of the sphere, you can get a volume. You know what oil you use, so you know the density, and you can calculate the mass from just the shape and the density of the oil droplet. So that's something you can figure out. G is 9.8. set plate separation you know, voltage you know. He solved for the charge of the electron and found through very careful observation and repeated experiments that the charge of an electron was negative 1.60 times 10 to the minus 19 coulombs, which is very close to the value we have today using much more sensitive measuring tools. Well, now that you know the charge of the electron, and previously we know the charge ratio from the electron to the mass of the electron from, I believe, Thomson, plugging in those values, we find the mass of the electron is 9.11 times 10 to the minus 31 kilograms. Tiny. Very, very tiny. Compared to the mass of a proton, 1.67 times 10 to the minus 27 kilograms, a proton's more than 1,800 times more massive than an electron. That was kind of surprising because protons and electrons have the same amount of charge, but one is significantly more massive than the other. And how is this mass distributed in the atom? That was something that wasn't known about until a scientist named Rutherford started experimenting with the charge in an atom. Early on, it wasn't known how the positive charges were distributed in an atom. They knew electrons could be little tiny, very low mass particles, much smaller than the mass of even the lightest atom, hydrogen. But it wasn't known how the positive charge was distributed in an atom. And the initial idea was called the plum pudding model, where the atom itself, they thought of as sort of just this mass of pudding, and then the electrons would be plums, or little particles, that existed in that pudding. Sorry, the electrons. So the pudding would have a general positive charge, and the little plums, little solid electrons, would have the negative charge, carrying the negative charge in that atom. So to test this, scientists named Rutherford decided to create a very thin sheet of gold foil. And gold is an incredibly malleable metal. It's very easy to make very, very thin sheets of gold. So the yellow dash here shows a very thin gold foil, only a few dozen atoms thick. And incident upon that gold foil, Rutherford created what's called an alpha source. An alpha particle, we'll learn when we talk about radioactivity in a few chapters. Alpha particles are a type of radiation. It's actually a helium nucleus stripped of the electrons. So it's 2 protons and 2 neutrons. So think of it like a little bullet, a little positively charged bullet flying towards the gold foil. What they expected would happen in the plum pudding model was that an alpha particle will get slightly attracted to the negative charge in the plum pudding model, but it would deviate very little as it passed through because an alpha particle is also significantly massive. So it's about 7,000 times more massive than an electron. So it really wouldn't be affected by the electrons, right? It's like throwing a car at a baseball, right? The baseball just is not going to do well in that situation. Surprisingly, what was found was that a lot of the alpha particles, most of them passed through, again, very little minimal deviation, but some of them bounced off of the gold foil. And the analogy given by Rutherford, it's as if you shot a cannonball at tissue paper and had the cannonball bounce back. How is that possible? How is it possible for this heavy, positively charged alpha particle to bounce off of pudding, right? The only way that this works is if the positive charge, it can't bounce off the electrons are far too low mass. The only way this works is if all the positive charge is concentrated in a very small volume. They call that small volume the nucleus. So this led to the beginning and the incorrect model of the atom, which you've probably been taught, the planetary model, where atoms are thought to be like little solar systems. where the positive charge, the nucleus, and of course the neutrons that hold that positive charge together, the nucleus of the atom is where most of the mass is. Just like in our solar system, the sun is where most of the mass of the solar system is. And the electrons are little planets orbiting around that nucleus, just like planets orbit the sun. This is an incorrect model. But even though it's incorrect, we will talk about it because it does help people understand, especially electron transitions, how electrons can jump energy levels. It's easier to think about the planetary model of the atom when you do those types of thought experiments. So this is the planetary model of the atom. We'll talk about Bohr's model in a bit, and then talk more about Schrodinger's model later on in this chapter.